So let G composition be a semigroup in which all left multiplication maps are surjective and there exists an element B in G for which the corresponding right multiplication map by that element is surjective. Then G becomes a group. In a monoid G composition, for every element A in G, either the left multiplication by the element A is surjective or the right multiplication by the element A is surjective. Then G composition is a group. In my previous video, I explained how the cancellation laws in a groupoid is not just a property of equations but a reflection of the injective nature of the multiplication maps. Today we will see the interplay between the surjective nature of the multiplication map and the group structure on a semigroup. Let us start with an interesting result. So assume a semigroup G composition has a right identity element E, and for each A in G there exists an element B in G satisfying A compose B equals to that right identity E. Then G composition is a group. So what is given to us? Given it is a semigroup and we have to show it is a group. So we only need to prove that identity element exists and every element is invertible. So basically we only want to prove that this right identity is in fact the identity element of this semigroup and this B is actually the inverse of A. Okay, so let's see the proof now. So let us fix an element A in G. Then by assumption there exists an element B in G such that A composition B equals to identity. Similarly, for this element B there is another element C by the same assumption such that B compose C is the right identity element E. Okay, so we have A composition B equals identity and B composition C is not the identity, right identity, and B compose C is also the right identity E. Now let's see what is this quantity B compose A. So B compose A equals to, by the property of right identity of E, B compose A compose E, and we know that E is also B compose C, just replace E by this B compose C, and then by associative property we may write it like this: B compose A compose B compose C, and A compose B is that right identity E, so that B compose E compose C by associativeness, and B compose E is B because E is right identity, and then B compose C is again E, which means A compose B is same as B compose A, and that is your right identity element. So basically once you show that, once we prove this E is actually the identity element, then we can claim that B is the inverse of A. So let's see what it means to show that E is also the left identity element, right? So basically let's start with this quantity E compose A, and then the value of E is given by A compose B. So A compose B compose A, again by associative property A compose B compose A, and B compose A is E. Just now we derived this, so it becomes A compose E, but E is right identity, so A compose E is A, and therefore we have E compose A equals A compose E equals A. And since A is arbitrary, this implies that E is the identity element in the semigroup G composition, and therefore it becomes a monoid. So only thing remains to prove that every element is invertible, and that follows from A, because here it shows that B is the inverse of A. And since A is arbitrary, every element in this monoid is invertible, and therefore it becomes a group. Now I would like to make a remark on this result. What if right identity element E exists, and for every element A in G there is an element B in G satisfying the other way around? I mean B compose A is that right identity. That means every element has a left inverse with respect to this right identity element. Then still can we say that is a group? Let us have this remark now. So here G composition is a semigroup having a right identity element E, and for every element A in this semigroup G there exists B in G satisfying B compose A equals to identity. Then G composition may not even be a monoid. Let's have some example. So we consider G equals to 0, 1 and define star on G by A star B equals A. That is basically projection on the first component for all A, B in G, and clearly it is a binary operation on G. And then we note that A star B star C equals to A by the defining property of star, just projects on the first component. Likewise A star B star C equals, so this is A star C, again this is equals to A. That means these two are equal for all ABC in G, and therefore this star is associative, and hence G star is a semigroup. Moreover, we can see that 0 star 0 equals to 0 and 1 star 0 equals to 1. Therefore, this 0 is actually playing the role of a right identity element. And 0 star 0, that means for 0, this 0 is the left inverse, short of left inverse, and similarly for 1, 0 is the left inverse, because their star will give you the right identity element. So these criteria are all fulfilled, but yet it is not even a group, not even a monoid, because here identity element doesn't exist. So suppose there exists an identity element, let's call it to be E. Then what is the meaning of that? Then E star 0 equals to, so since E is identity, that is equals to 0. By the defining property of star, this is also equal to E, just projects on the first component, which means E equals to 0. By the similar argument, we could have shown that E equals to 1, which means 0 equals to 1. So which is certainly not the case, and therefore identity element doesn't exist in the semigroup. So it is not even a monoid. Now we'll see couple of nice interplay between the surjective property of the multiplication map and the group structure. So let G composition be a semigroup in which all left multiplication maps are surjective, and there exists an element B in G for which the corresponding right multiplication map by that element is surjective. Then G becomes a group. So here it is given that G composition is a semigroup, and we want to prove that this is a group. So all you need to show that identity element exists in this semigroup, and every element in this semigroup is invertible, right? Okay. Now given that LA is surjective for all A in G, so in particular LA is surjective for A equals to that specific element B, and that is actually the starting point of the solution. So LBG to G is surjective, which means the element B also has a preimage here. Let us denote this by this preimage by E. That is, there exists an element E in G such that LB of E equals to B, which amounts to say that B composition E equals to P. And the reason behind calling this preimage E is pretty clear, because here E is doing exactly what identity element does. And once we preimage, once we precompose by an arbitrary element X, then we found this, and after associativity it becomes X compose B compose E equals X compose B for all X in G. Let us denote this by equation A. Now let's take an arbitrary element A in G. Now given that this right multiplication by B is also surjective, so in particular this element A has a preimage. Let us denote this by Y. So there exists Y in G such that RB of Y equals to A, which means Y compose of B equals to A. Now this A holds for all X in G. So in particular when X equals to Y, this is true. So if you replace X by Y, then we obtain Y compose B compose E equals Y compose B. But Y compose B is exactly A, which means A compose E equals A, which amounts to say that, well, here A is arbitrary element, which amounts to say that E is actually a right identity element in the semigroup G composition. Also, for any A in G, this LA is surjective. That means for this element, for this right identity E, there is a preimage. That means there is some B in G such that LA of B equals to E, which means A compose B equals to E. That means G composition is a semigroup in which right identity element exists, and for every element A in G, there exists another element B in G such that A compose B is the right identity, and therefore it is a group by our previous observation. Well, now we'll see another nice application of the surjective property of the multiplication maps. In a monoid G composition, for every element A in G, either the left multiplication by the element A is surjective or the right multiplication by the element A is surjective, then G composition is a group. So to see the solution, so all we need to prove that every element here in this monoid is invertible, right? Because it is already a monoid. So let's take an arbitrary element A in G. So let A belongs to G. So one of LA and RA is surjective. So without loss of generality, let us assume that LA is surjective. Okay, so identity element also has a pre-image. So let us denote this by B. So then there exists B in G such that LA of B equals the identity element, which amounts to, say, A compose B is the identity element. Let us denote it by equation 1. So now it suffices to prove that B compose A is also identity, right? Okay, so now let's think about the element BA, that is B compose A. So one of L subscript B compose A, I mean left multiplication by B compose A or right multiplication by B compose A is surjective as per assumption. So then either L B compose A surjective or R B compose A is surjective. Now you consider two different cases. So what happens if L B compose A is surjective? So let's say case 1. So assume L B compose A is surjective. Okay, so let's see how can you decompose this L B compose A. So note that for any element x in G, L B compose A of x is basically B compose A of x compose x, which means B compose A compose x. So that is basically LB of A compose x, which means LB compose LA of x. And this holds for all x in G, and therefore as a function LB compose A is equal to LB compose LA. Thus LB compose A equals LB compose LA. Now since this function is surjective, so is this one. So this would mean LB is surjective. So there is a pre-image of the identity element. So then there exists C in G such that LB of C equals to identity element. That means B compose C equals to identity element. Okay, now we have in 1 that A compose B is identity. So just simply I apply the associative property by associative property. A compose B compose C is same as A compose B compose C, which means, so B compose C is identity here. So it is A compose, this side A compose identity, and in the RHS A compose B is identity. So identity compose C, which means A equals C. And therefore just we replace C by A in this equality, we would have B compose A is identity. Let's give it equation 2. So from 1 and 2, A compose B equals B compose A is the identity. And that implies A is invertible. So this is in case 1. So another possibility is that this RB compose A is surjective. So let us try to analyze this case as well. So now we assume that RB compose A is surjective. Okay, so just like before, let us try to see how can you break this composition. I mean this function as a composition of two functions. So note that for any x be in G, so what is the effect of this function on x? RB compose A on x equals x compose B compose A. Then by associative property, this becomes this, and this further becomes RA of x composition B, isn't it? Well, again this becomes RA of RB of x, this quantity. So it is basically RA compose RB of x, and this holds for all x in G, and therefore as a function this is same as composition of these two. So this should mean RB compose A equals RA compose RB. Now we are assuming that in case 2 assuming that this function is surjective, and therefore this outer function RA is surjective. So this should mean RA is and that means there exists an element, then there exists an element let's say D in G such that RA of D is the identity element, such that RA of D equals identity element, that is, which amounts to say so decompose A is the identity element. Okay, so we have A compose B is identity here, now we have decompose A is identity here. So things are around A. So by associative property, we have so decompose A compose B equals decompose A compose B. Now A compose B is identity, so it is basically left hand side becomes decompose E, and the right hand side becomes decompose A is E, so E compose B, which means D equals B. That means we can replace this D by B so as to obtain B compose A equals identity. Let's call it equation 3. So from 1 and 3, we have A compose B equals B compose A is identity, and that amounts to say is invertible. Well, so we have shown that in either case that A is invertible, and this completes the proof actually, because it was already given to be monoid and every element is invertible, and therefore it is a group. Now we'll see another interesting thing. Now we have the definition of idempotent element. So an element A in a groupoid G composition is said to be an idempotent element if A square equals A, that is A compose A equals to A. For example, you can see that 0 and 1 are the idempotents in this monoid Z dot, because if we consider that defining property of idempotent, which means A square equals A here, so here it is normal multiplication, usual multiplication, and that would mean A times A minus 1 equal to 0, and it has exactly two solutions, namely 0 and 1. So in fact 0 and 1 are the idempotent elements, precisely the idempotent elements in Z dot, whereas 0 is the only idempotent in Z plus, because here this operation is addition, so a plus a equals a, that would mean 2a equals a, and that would mean a equals 0. Now we'll see another example. We'll see an example of a finite monoid that is not a group. So now we consider g equals to 0, 1 as a subset of real numbers, only to have some order relation between the elements here. Then we define a binary operation star on g by a star b equals to minimum of a and b. Indeed, it is a binary operation, and moreover it is commutative, right? Okay, and also for any three elements a, b, c in this set, if any one of them equal to 0, then a star b star c equals to 0 by this minimum thing, and similarly a star b star c equals 0. Otherwise, when all a, b, c are equal to 1, all of them are equal to 1, then both of them are equal, because both of them are equal to 1, which means a star b star c equals a star b star c for all a, b, c in G, and therefore this star is associative binary operation on G. Also 1 star 0 equals 0 star 1 because of this commutative nature equals to 0 because minimum is 0, and 1 star 1 equals to 1, which means here 1 is actually the identity element, and therefore this semigroup is actually a monoid. But here 0 is not invertible, because 0 star 1 is 0 and 0 star 0 is also 0. So we are not getting the identity element by any means, and therefore 0 is not invertible element in this group, in this monoid, and therefore it is an example of a finite monoid that is not a group. But in our context, note that here this 0 star 0 is 0 and 1 star 1 is 1, which means both 0 and 1 are the idempotent elements. Now we have a very relevant result along the lines of this idempotent element. So now we see this result. So let G composition be a finite monoid, then G composition is a group if and only identity element is the only idempotent element in G. So let us prove this now. So first we prove that this G is a group, then that would imply identity element is the only idempotent in this group. So basically it has two components. First is showing that identity is an idempotent, and then it is the only. So first thing is pretty clear because E compose E is E, and therefore E is an idempotent element. Now we assume any element A in G to be the idempotent, and then that would satisfy A compose A equals A. Then we precompose by A inverse so as to obtain this, and then after application of associative property, it becomes E compose A equals E, that is A equals E, which means E is the only idempotent in G. And in this implication, we don't need this finiteness of this monoid or group. So this actually holds in any group. Now let us try to prove the other implication, that given that in a finite monoid, identity is the only idempotent, then it is actually a group. So well, it is given already a monoid to, so basically all you need to show that every element is invertible. So let's take an element A in G. Then A square, A cube, these are all elements in this finite monoid, and they can't be all distinct, certainly because it is finite. So certainly there are indices m and n, natural numbers, such that a to the power m equals a to the power m plus n. Now we wish to show that this element a to the power m times n is actually an idempotent element. To see this, we need some adjustment like this. So a to the power mn can be rewritten as a to the power m times n minus 1 plus m, which will give us mn. And then we can break it like this: a to the power m times n minus 1 compose a to the power m. And now we replace this a to the power m by a to the power m plus n so as to obtain this thing. And again, after applying this associative property, we'll have a to the power m n minus 1 plus this m composition a to the power n, and this is our a to the power mn composition a to the power n. So a to the power mn equals a to the power mn compose a to the power n. If we repeat this again, then we can replace this a to the power mn by this expression so as to obtain a to the power mn compose a to the power 2n. So after repeating this process m times, we would have reached a to the power mn compose a to the power mn, which means a to the power mn is an idempotent element in this finite monoid. But is given that identity is the only idempotent elements, and therefore a to the power mn has to be the identity element, and that means a compose a to the power mn minus 1 is equals to a to the power mn minus 1 compose a equals to identity, and therefore a is an invertible element in this monoid, and a is arbitrary, therefore this monoid becomes a group. Now we have a remark. Note that this finiteness is really important, because if we consider the set of all non-negative integers with respect to usual addition operation, then we have already shown before that it is a monoid, but it is not a group, because non-zero elements doesn't have the additive inverse here. But here 0 is the only idempotent, yet it is not a group. So this finiteness is really a important requirement. Well, let us conclude with this, and thank you for watching this video. See you next time.